What does our beautiful planet have in common with white dwarfs? Remnants of dead stars. Those who know anything about white dwarfs might right away say the size. And that's correct. In spite of a huge mass difference, white dwarfs are comparable with the Sun in mass. They're similar in size with Earth, which makes white dwarf matter one of the densest in the universe. Obviously, they also have similar shapes. Well, not everyone would agree, if you know what I mean. As all of the massive enough objects, they are almost spherical with a certain level of ellipticity.
But that's not what I'm talking about.
Perhaps similar processes inside both Earth and white dwarfs may generate magnetic fields.
Let's first talk about magnetic fields in a bit more detail.
Magnetic fields are not an uncommon topic while talking about stellar remnants such as white dwarfs and neutron stars. After all, there is a whole separate type of neutron stars called magnetars because of their insanely powerful magnetic fields. White dwarfs also may have magnetic fields, sometimes 1,000,000 times more powerful than Earth's magnetic field.
But how do we even know they have powerful magnetic fields?
In the solar system, we can send a spacecraft with a magnetometer, let's say to Jupiter, and measure properties of its magnetic field directly. Spacecraft like Galileo, Cassini, Juno had or have magnetometers, but we haven't reached other stars, if we ever will. And in most cases, we see them as point sources, and stellar remnants are tiny compared to main sequence stars.
But anyway, it is possible to measure properties of magnetic fields of other stars by using Zeeman Effect.
As many of you probably know, stellar light can be broken into multiple wavelengths with special equipment. It's basically the same how a regular prism works. The spectrum we get as a result can be continuous, or there can be emission lines, for instance when we observe the emission of a gas in a cloud. Or absorption lines, when, let's say, stellar light goes through some medium, gets absorbed and then re-emitted. Those emission and absorption lines are unique to different chemical elements. So what's the Zeeman effect? Spectral lines that are normally singular, in the presence of a magnetic field, get splitted into several components. Also, in the presence of a magnetic field, the light becomes polarized. So using spectropolarimetry, it's possible to remotely measure properties of magnetic fields of distant stars or stellar remnants.
And white dwarfs have indeed been discovered to have strong magnetic fields. And here's the problem. We're not quite sure how they actually occur.
For white dwarfs, several mechanisms of how a magnetic field can form were suggested, but the problem is none of those explain perfectly every case. Various white dwarfs, single or in binaries, can have very different magnetic fields. A study that recently came out in Nature Astronomy focuses on dynamo mechanism for white dwarfs. Authors claim that this mechanism explains formation of magnetic fields in white dwarfs very well. And what is interesting here is that it is the same mechanism that is believed to work here on Earth. But how can magnetic fields be generated the same way in objects that are that different?
First, let's look at the modern theory of how Earth's magnetic field is generated. By the way, I can easily imagine how people who are not very interested in all of this would say something like, "What? Magnetic fields? Who even cares?"
And yet, without a strong magnetic field of our planet, there probably would be nobody to question whether this topic is interesting or not, because our planet would be unprotected from solar wind, Earth could lose atmosphere, and so on. Okay, our planet cannot have inside a permanent magnet like this one.
If you know anything about magnets, you might be aware of the fact that permanent magnets cannot exist at high temperatures of the Earth's core. So we need a different mechanism, and it is described by the dynamo theory.
Inside Earth, there is an iron-nickel core that consists of two layers, solid inner core and liquid outer core. In the electrically conductive flows of the liquid core that is constantly moving, the magnetic field is generated.
I have to say that we are not 100% sure that this is exactly what is going on, but that's currently a leading theory. That's all great, and yet it might not be clear how it all works.
How do electric motors work? Well, in short, a coil of wire is placed in a magnetic field and then electric current is passed through the wire. It becomes an electromagnet and starts spinning, but it also works the other way around. According to Faraday's law of electromagnetic induction, if we start spinning a coil in the magnetic field, we can generate electricity. A simple example of that is a bicycle dynamo, which is used to power lights on a bike. Mechanical energy of a wheel spinning is converted into electricity.
And the electric field generates magnetic field. So to generate magnetic field, we need some material in motion that also conducts electricity.
So inside Earth, instead of a coil of wire, there is a liquid layer of iron and nickel. But the coil also has to rotate. How does the Earth's core move? Well, first of all, the core rotates with the Earth. And secondly, there are convection currents. Sure, the core is hot, but it's cooling down over time. That's why the solid inner core is constantly growing, because iron sinks down and becomes a part of it. And the lighter elements instead form upward convection currents, and that creates constant movement of material in the core.
Well, great. Conductive material, check. Motion, check. Feels like I'm missing something. In bicycle dynamos and generators, there is already a magnetic field provided by a permanent magnet, for instance. Without it, nothing would work. That's why for Earth we need the third ingredient, seed magnetic field, that would kickstart the dynamo mechanism.
For instance, it can be a magnetic field of the Sun. That does affect Earth.
Obviously, it's a little more nuanced than that, but in general it looks something like this. So what about white dwarfs?
When the star ends its life on the main sequence and leaves a white dwarf, at first it's a hot, dense ball of mostly liquid carbon and oxygen. Then its destiny is to gradually cool down over the span of billions and billions of years. While cooling down, the insides of a white dwarf can begin to crystallize, so it's slowly turning into a huge crystal. So it also forms a solid inner core that grows.
This already is beginning to look like what we see here on Earth, or inside of it, but with different elements, at different temperatures, pressures, and so on.
And we get a crystal solid core surrounded by electrically conductive fluid, and solidifying core can also create convection currents. And because of the conditions that are that extreme, the resulting magnetic field is orders of magnitude stronger. The mechanism not only explains the white dwarf's magnetic fields, but also their diversity.
Thanks for watching. Links to all of the sources are down below in the description, and if you enjoyed the video, leave a like, comment and subscribe. Bye!